Hey guys, this is Alex Panner, Physics 2211 MO8 Lab 9. And our main problem was to model a 2D spring using VPython. And the chief result was that for a very short period of time, VPython can model a 2D spring, and the periods of oscillation can be calculated. So we uploaded a video onto Tracker and used it. So the total time of the video was 9 seconds, and the time between frames was about 1 over 10.5 seconds. And the origin is at the fixed attachment, and the positive x direction is pointing that way. So the spring is in the negative y. And the scale, we used the spring's length, and it was 0.7 meters. And here's my, oh, and then I use a point mass system to track the position over time, and you get the x and y here, which we then saved as a CSV, and we used it in our VPython. And here's my model, and you can see some of the initial conditions: the mass 0.402 kilograms, the initial position, the initial velocity, which is 0 because it started from at rest, the constant, and then the total time. Since I did the whole video, it was 9.307 seconds. You can see potential energy and kinetic energy. Oh, potential energy of gravity. Let's see, force of gravity, force of the spring, the net force, and this is what it looks like. So you can see there's a pretty good model. The VPython model is the orange ball, and the actual experimental data is the blue ball. And then for our first problem, we wanted to calculate the oscillation period in the y direction. So I used this graph, and I went from peak to peak, which is one oscillation. And if you click on it, you can see the x values are the time. So you can just subtract the time of the two peaks from each other to get the oscillation period. And then I did the same for the x position, and this is what I did pretty much. This is what I got. So in the x of the simulation, you can see it's 1.666 seconds. For the actual data, it was 1.45, and those are pretty much almost the same, which they're supposed to be. And then the period of oscillation in the y direction for the simulation was 1.526, and for the actual data, right here, it was 1.513, which are again almost the same. However, the oscillation periods between x and y do differ, which makes sense because if they were the same, the weight would move more uniformly. And we can see here that it's kind of moving all over the place. And they differ because in the x direction, it's more like a pendulum, and in the y direction, the spring force has a greater impact. So it's two different periods of oscillation. And as for my graphs, let's take a look at the x one. This one is the model in the x for the x direction. So you can see this one models it pretty decently as well. And our second problem was about the energy principle, and you can see on my graph the blue line represents the total change in energy. So you can see that the energy principle is satisfied because the sum of delta K, delta U of gravity, delta U of the spring, which those are potential energies, is equal to 0. And then For our last part, the question is, when defining gravitational potential energy in your computer model, you made a choice for the origin and you change the location of the origin. So changing the location would only change the positioning on the graph. So this would be changed. Well, this one's X, so the Y positioning would be changed. But the actual physics will remain the same because it's calculated based on the change in position, which would still be the same.